Okay. Yeah. Hi, everyone. Can you hear me?
Yeah, I can
And
hear
see my
you.
screen?
Yeah, and we see the slides.
Okay. Cool. Right. So thank you all for having me here at this conference. Unfortunately, Chiara couldn't make it. She broke her arm, so I'm giving a talk on her behalf, and also on behalf of the nanograph collaboration. Unfortunately, I realized that I'm not going to talk about neutrinos at all, so I'm sorry for that. I still hope you'll be interested in pulsar timing arrays and gravitational waves. So the first thing I want to show is a very schematic overview on how pulsar timing arrays work, and it's also like my one slide summary. So if the rest is like too complicated, if you remember only that, then that's already good enough. So as any experiment, you need some instruments to run. And so I'm using the nanograph as an example, but you can replace the telescope with other telescopes. We use the Green Bank telescope and the Arecibo telescope. And from those two telescopes, we can get observations of pulsars. These are going to be reduced into a data set, which you can see on the top. This is from the 12.5 year paper. Each of those points is like an observation, and the time span on the x-axis is like 12, 13 years. And there's a number of like 45-ish pulsar that we observe. And this data is sort of continuously expanding. We plan to include the VLA and Chime into the dataset in the near future, and add more pulsars into the observational dataset. And the next step is, once you have the observation, you have to do some analysis on the data, and you reduce some signal that you are interested in. And for us, it's gravitational wave signal, which is like a common signal amongst all of these pulsars. And so I'll mainly be talking about common processes. So it's a signal that affects all of these observations for each pulsar. And so you should see a correlated signal across all of them, which is shown here on the right. So you have a correlated signal here, which sort of appears at the lowest frequencies. And that translates into like a nice close contour for the power law if you were to draw a power law across all of these points. And then finally, you can take this information that you've detected something, and you can try to do some astrophysics interpretation. So because I'm like a massive black hole binary type of person, I'll mainly talk about the massive black hole binary interpretation of that. But that's not necessarily the only explanation that can be explaining what we see in the data. And finally, this is the actual detection of gravitational waves, and that sort of motivates us to keep on going, to do more observations, and hopefully that has a broader impact on the science. Right, pulsar timing. So pulsar timing, we observe pulsars, which are rotating neutron stars, where the rotation axis and the axis of the magnetic beam is sort of misaligned or not quite aligned well. And so as the pulsar spins, there's a chance that the beam of radiation sort of points towards us, and then it rotates away. And so we get like a pulse every time the pulsar rotates. And if the pulsar rotates like a few hundred times per second, so with millisecond periods, those pulsars are very stable, and so we get a pulse very regularly. And you can time those. So you use your telescopes, you observe a given pulsar, and then you see in black the pulse that you get from the pulsar, and you can model the arrival of these pulses. So you know where the pulse is on the sky. You know, roughly speaking, the mass. It should be periodic. So you have the red, which is your model predictions, and then you compare those predicted ones against the actual observed pulse. So the time when you actually see the signal from pulsar, these are the black. And then if you have some sort of unmodeled noise that you didn't account for, you will see that some pulses arrive earlier than you expect and others arrive later. And this could be due to some gravitational waves that we've not put into the model yet. And so going to gravitational waves is a schematic to sort of show all the different things you have to like consider and take into account when you try to do Pulsar timing array analysis. So for example, if a parser, some parsers are in a binary, so you have to model the parser itself and its companion and the period of this binary and so on and so forth. And then the radio signal that the parser emits, they have to travel through space basically to us. And so for that, they have to travel through interstellar medium, so they can be deflected by electrons along the way of sight between us and the pulsar. And they can also travel through some gravitational waves, like for massive black hole binaries. And then they have to travel through the solar system, where we then finally detect them on Earth with our radio telescopes. And along all of these, you can see that there are several effects that can sort of give you some signal that sort of makes a prediction of a regular space observations sort of not correct, and to just observe one parser and be sure that whatever you see is from gravitational waves is quite difficult when you have a bunch of other things. And so that's why we have to observe a lot of parsers. So if you have a different parser in a different location in the sky, that one will be it will be a different parser. So whatever kind of process happens at this parser will be different from whatever happens at parser A. The radio parsers travel through a different path in space, so the interstellar medium will be different. But what will be the same is the gravitational waves, if it's sort of like a background in space-time. So this would be the similar signal. And then it goes again through the solar system and to us on the telescope. So yeah, you also need to know the solar system very well, because that's also like a common path that all the signals have to travel. And so in the gravitational wave spectrum, the PTA is here. So it's in the nanohertz frequency regime. We mainly look at massive black hole binaries, primordial black holes, and other exotic sources in this regime. This sort of complements well the LIGO interferometer, which have already detected black hole mergers, neutron star mergers at the sort of tens of hertz of frequencies. Intermediate between the two is the LISA band, which is the millihertz one, which is supposed to launch in 15 years or so, 12 years or so. And then at the very low frequencies, you have CMB observations. And so this is sort of like the gravitational wave spectrum, if you wish. And our window that I'm focused on in this talk would be the PTA window. And that we hope we will open in the very near future. I have this one slide to sort of bridge into the data analysis and the sort of schematic description of PTAs. So in simple terms, we model all of those signals as like a Gaussian process. I have this green box here, which says the time model is marginalized. The timing model here refers to all the parameters that we associate to the pulsar itself. So the pulsar mass, the pulsar companion mass, where the pulsar is in the sky, and these kinds of things. So this we know where the pulsar is, and we sort of model that away. And so the remaining things are these four sort of broad categories of noise terms. So you have white noise, which is just instrumental noise. You have the red noise, which is unmodeled noise at a given pulsar. You have dispersion measure, which is the noise that you get from the pulse traveling, the radio pulses traveling through interstellar medium. And then you have the signal from gravitational waves, which is the one that we hopefully want to detect. And so this is what we did with the nanograph 2000 hybrid data set. We took the data, we analyzed it, and we looked specifically for this part, the gravitational wave bit. And we found something which in frequency, and this is the sort of delay. So it's the amount of time that the pulse shifts. So basically in frequency here at the left end is like 1/12 years. So on average, pulses that are about 12 years apart, they have like a delay between them of 10 to minus 6 seconds, so roughly a millisecond or so. That's like a very long-term thing. So as you get to higher frequencies, that means you look at observations that are close by, you are more dominated by white noise. So if you look at like observations that are a week or so apart, then you have some variation of the order of 10 to minus 8 or so like tens or hundreds of nanoseconds. And hopefully we see that in the lowest frequencies, you see some sort of excess power rising. So you have more deviation than you would expect from just white noise from the instrument. And that's the common process that we've seen in the NanoGraph 12.5 data set. And this translates into like a power law that you can model here on the right with the spectral index and the amplitude. And here are just some equations that sort of relate these terms to the characteristic strain of gravitational waves. And if you fix the amplitude here at this dashed line here, which is 13 thirds, which corresponds to massive black holes that are circular, you can find an amplitude of about 2 10 to the minus 15. Right. And but this is just a common process. So it's not it's a hint of gravitational waves, but it's not definitive evidence for it. So the definite evidence is that you have to make sure that this process you see in different pulsars is correlated in a specific way that's characteristic to the gravitational wave. And this is known as the Hamilton-Downs curve, which is sort of shown here in this dashed blue line on both figures. And ideally, you want to see that that this is the amount of correlation. And this curve is a function of the degree of separation between two pulsars. So if you have two pulsars that are some angular separation away, then you would expect that the correlation between them is some amount of power. And you can see that we don't really see like the points here on the left, as well as the contours in the gray on the right. They are not really like in that following that blue dashed line. So there's some evidence that can be the case, but you can also see that if you just draw a straight line through here, you can also match those observed points. And similarly, if you like move this orange one down a little bit, you can also draw like a straight line through those. So this is not a detection of gravitational waves yet, but we hope that we can, with more data, we can sort of close in on the blue line and hopefully have a detection soon. All right. Just to go a bit further, NanoGraph is not the only sort of PTA collaboration in the world. There's a few more. So in NanoGraph, we have the Arecibo, VLA, Greenbank, and Chime that observe, and we use the data from those. Unfortunately, not from Arecibo anymore, but there are still some observations that we have yet to analyze. In Europe, the European Pulsar Timing Array, there are 5 telescopes: Effelsberg, Giotto, Westerbork, North Sardinia, and there's also LEAP, which is sort of coordinated observation between these 5 telescopes. So you can sort of add them up and have like a 6 more sensitive telescope. And then in Australia, there's the PPTA, the Parkes Pulsar Timing Array, and they have the Parkes Radio Telescope. These 3 here are sort of and I forgot about that. The Indian PTA with the GMRT, they have recently joined the IPTA. So now these 4 PTAs are sort of all part in the International Pulsar Timing Array group, and we have collaborations with Meerkat and FAST to sort of get those instruments also in the family of the IPTA. Now the IPTA will also combine the dataset from each of the PTAs, and the recent one dataset is data release 2, and we also analyze that for some common process. So this is preliminary, so yeah, please don't like I don't know, share this, but it's also not a detection of gravitational waves. We sort of strengthen this signal that we see at like low frequency compared to the NanoGraph one. So on the left, I plotted the NanoGraph contours that you saw before in red, and the blue are the contours that you get from the IPTA. And on the left, you can see that the time span is longer, so you can reach into lower frequencies, and you see that the sort of excess or the extra power that you see is sort of still there. Right? So you see more deviations away from just white noise. And on the right, you see a sort of contour for the power law that's now closed. It's a little bit different from the nanograph 12.5-year contour, but they're sort of still consistent at the 2-3 sigma level, and they intersect at roughly the 13 thirds, where we expect the gravitational wave background to be from massive black hole binaries. If you look at the amplitude at this line, it's about 2 for nanograph, sorry, and 3 for the IPTA. So there's some small tension, but we hope that with more detailed analysis, that is in preparation, we can sort of have a more understanding on what the difference are. Right, I have like 10 more minutes or so. So the following, I'm going to get some astrophysics interpretation. As I said, I'm a massive black hole binary guy, so that will be my focus. But you could imagine that this could be from some other sources as well. Oh, right. Oops, I forgot about this. Yeah, you can also translate these. So the left here, you can translate this into the strain space, so your frequency versus characteristic strain, or the omega space, where you have the gravitational wave energy density. So these three are sort of all equivalent, and there are some formulas that sort of relate the three of them. Right, going into astrophysics. So the prime candidate that we're looking at are supermassive black holes. So those are black holes that have masses more than 1 million solar mass. For example, the one that was photographed by the AHT, the M87. And so we know that black holes must exist with that mass, and they are most likely in a lot of galaxies. And then we know that galaxies sort of merge. So whenever two galaxies merge, the two central black holes, they also have to interact with each other, and they are likely to also merge, form a binary and merge and emit gravitational waves. And this is the gravitational wave that we are hoping to find with pulsar timing arrays. Right, so there's one way that I've mostly worked on in the past is a parametric model. So you model the population of massive black hole binaries in the universe with some parametric description, and you pair that with the emission of energy that each of those binary emits in gravitational waves. And you basically just multiply them and sum them up over the mass and redshifts. I will not focus on this energy emission of an individual binary, but I'll just focus on the population. So the population, you can relate that, as I said, to galaxy mergers. The 4 blocks that I have here are sort of the key ingredients to that. So one, you need to know how many galaxies there are in the universe. You need to know how many of those galaxies are in pairs, how long the merger will take, and then finally you have to relate the galaxy with a black hole, and this is done with the M-galaxy and black hole relations. So you can do that. You can make a prediction on what gravitational wave emission you expect. So this is done in the green contours here on the left from basically a sample of populations, of possible population of black holes in the universe. And then you can overplot the contours again from the IPTA and the non-graph contours. And you can see that they are consistent with what we predict from massive black hole binaries. And that's a good sign. And then on the right, you can also produce some expected parameters, how a detection of this level here, about 2 or 3 10 to the minus 15, would mean for the population of massive black holes. And here I'm showing the 4 parameters, which is the merger time. So you see that mergers have to happen within some gigayears, 3 gigayears or so. The alpha and beta actually relate to the merger time. So they both go to the low end, which basically means that you have to have more mergers happening quickly. And then finally, this M star here relates to the mass of black holes. So the 8.4 here basically means for a reference galaxy with 10 to the 11 solar mass, you need to have a central black hole of mass 8.4, 10 to the 8.4, which is like 6 and which is quite heavy. And this green here sort of is a contour that comes from all the observation data that we have. So you can see that if the detection of the null graph and IPTA is really from gravitational waves and is from massive black holes, then that would mean that we need very heavy black holes. And this translates altogether into like a overall merger rate of 10 to minus 4 per megaparsec cube per gigayear. Now, and alternatively, you can also go and use gas catalogs and simulations to sort of get an estimate on the merger rate. So this is what Chiara and her collaborators did, starting from 2017, and it's sort of still continuing. So what you can do is you can take a gas catalog, for example, the 2-mass galaxy distribution. That was chosen because they also have redshift measurements for each of those galaxies. So you know the mass and how far the galaxies are away, which is very useful information that we need. And then you can take some relations from galaxy black holes, populate those with binaries, and see what kind of gravitational wave strain they would emit, which is what you see here on the bottom. So here are shown the galaxies that sort of could be detected and the corresponding strain. The right top one is just showing a sort of sensitivity figure of how sensitive we can detect gravitational waves as a position of sky. That's mainly dependent with where the pulsars are in the array. And you see like a bright spot on the left, which is sort of the galaxy plane has like all the nice well-timed pulsars, and there's like a small gap, a blue region where we're less sensitive, which is the sort of a region where we don't have many pulsars, essentially. Right, I will go a bit further. And so the thing is, you can then take this population and you can make a merge rate out of that. And then you can compare that to the observed amplitude that we have. So that's done by Chiara's student, Andrew Casey Clyde, and they get like a merge rate of 3 10 to minus 3 per megaparsec cube. So it's a little bit larger than the analytic model before, but in principle, it's somewhat of the order of magnitude. Yeah. Right. And then finally, you can also use that information to look for individual black holes. So which black holes we can actually hope to detect gravitational waves, which could be a binary. One candidate was this I should have labeled it. This is 3666b. It's like a very well-known candidate that to host a massive black hole binary. And we use that to, we use the null graph data to sort of look for its mass of this binary, and we put like an upper limit, and that's consistent with what the mass was predicted from electromagnetic observation. On the bottom, you see like another like attempt to find black hole candidates that could be detected with PTAs, IPTA, SKA1, where you have the different sensitivity curves, and each of those yellow dots sort of a candidate where we have some periodic light curve that could hint that there is a massive black hole binary in this galaxy, and that could be detected with good enough PTA dataset. Right, and on the right is sort of the analysis of a recent analysis of nanograph led by Maria Caresi, which shows, which basically took all the like 200 or 300 galaxies that could host black holes observable for the nanograph, and basically looked at each of those and placed an upper limit on the mass of the black hole binary that this galaxy would host. Since we have not detected anything, that means we can place an upper limit, right? If there was a binary at this sky location which has a mass larger than whatever, and is close by, then we would have seen this in our data set. But because we didn't, that means that either there is no binary in this galaxy, or that the binary has to be of a lower mass. a bunch of other works that we do in nanograph, which is also very interesting. So
Siyuan, you have 4 minutes to wrap up, please.
Yeah, I'll finish very quickly. Yeah, so there's just a list of other nanograph work that we also do with the lead people here, and on the right is just the recent analysis of the 12.5 data set for gravitational transform phase transitions. So these 5 blobs here, they are the same sort of frequency detection I showed before, and you can try to fit those with phase transitions, with gravitational from phase transitions. Right. And just to give a brief, something what to expect for the future. We are working on a 15-year data set, and we have done like a recent simulation of what we could expect, and this is done in Paul et al. And you can see that this evolution of the Hamilton Downs curve is very encouraging. So we're here on the left, roughly at 12 years. We expect to be in the middle with 15 years, and in 20 years we expect to be very able to constrain the Hamilton Downs. And so, depending on how the actual data set will be, we hope to have a significant enough evidence for detection very soon. So just to have a summary, we've seen an amplitude of a common process of about 2 × 10⁻15. There's no significant evidence for Hamilton Downs, so it's not a gravitational wave detection yet. We compared it to other PTA collaborations, which gives a similar sort of detection in a similar amplitude. The IPTA has an amplitude of 3 × 10⁻15. You can interpret this with massive black hole binaries to get like a merge rate between 10⁻⁴ and 10⁻³ per megaquasar cube. We're looking for possible individual black holes that could then also be used for multi-messenger astrophysics. A lot of work is done in nanograph. We expect to have a breakthrough soon, and we're working on the 15-year data set and the next IPTA combination. Right, thank you very much.
So thank you, Siyuan, for the great talk. I think we have time for a couple of questions, so please send them through using the Q&A button. And maybe I can start with one. And I wanted to ask you if you plan to increase the number of pulsar that you observe, and by how many?
Yes, I should have made this. Yeah, so the 15-year data set that we're currently working on, it will increase the number of pulsars by between 10 and 20. So we have about 60 pulsars from 45. And that will also add like 3 more years of data. So we continuously are expanding the array and add more pulsars. And then if you combine it on the international level, you have even more pulsars, which are not observable in the US, for example, like in the southern hemisphere, where you have the Parkes PTA, that will add like more pulsars to the array.
Okay, and can you give us like a rough number if you combine all the pulsars, how many they are?
Oh, yeah, I don't really have a concrete number, about 100 maybe, if you're very optimistic, but yeah.
Okay, thank you very much.